So welcome back, everybody, and hope you had a great weekend. As you saw from the email, I was a little bit delayed with the weekly email with plans, and simply because I had some problems with accessing Canvas. And also there seems to be something strange with the schedule. But you find, just to quickly remind you, you find everything on the official website. And the schedule was actually changed a little bit, so I had problems editing it. And there's actually something which remains from last year about the change of auditorium, which was wrong. And I sent that as an email to everybody, so I hope everybody saw that. Also to remind you where you find all the information. So we have a GitHub site, and feel free to download everything and use it as you want. And if you want to go directly to the plans for this specific week, you have at the bottom here on the left part of the window, you have the weekly slides and the exercises. And we already got somebody who wanted to see the exercises for next week, so we're going to place them during the day today as well. But week 35, these are the exercises which we're planning for this week, and which also can give you an additional score of 1 point. So if you collect all these different weekly exercises, you have the possibility of having something like 10 additional points. Okay, so today I'm going to use again a mix of slides and essentially the Jupyter notebook, because we're going to run some programs as well. And then I will switch some now and then between the Jupyter notebook and the Blackboard/whiteboard. So the plan today, and if you had time to skim through the Jupyter notebook, is first a quick repetition from last week, and I'm going to use the Jupyter notebook to do that. Then we are going to look at the equations for ordinary least squares again, and this is something which many of you may have seen in a standard linear algebra course, but we are going to go through the derivation, and that links up with the first exercise this week. So the first exercise this week is a paper and pencil exercise, where we, in a way, are trying to remind you of how you calculate derivatives of vectors and matrices. And the material which you find in the Jupyter notebook is hopefully of some help when you're going to solve the first exercise set. And this is something which is useful for many, many reasons. So one of the main reasons is that we are always going to structure our data, the input data and the output data, as vectors or matrices or higher order arrays, which we normally call tensors of a given order. So typically today, we are going to see the way we are going to rewrite the input data in terms of this so-called design matrix, which we defined last week, and how we are going to actually implement the standard ordinary least squares method. And then when we're done with that, we are going to bring in some of the mathematical interpretations, which is also something which we find important, because then you have a deeper feeling of what is actually going on. And ordinary least squares works well if you can invert that matrix which we discussed last week. If you cannot do that, then there are ways to circumvent the problem. And one of these is actually given by ridge regression and also lasso regression, which are popular methods. And we are going to start discussing them as well. And unavoidably, we have to sneak in a discussion of singular value decomposition, which is a very important algorithm in linear algebra and the analysis of what ordinary least squares is doing for us. So today is going to be a kind of mix of linear algebra, some practical implementations so that you can see how you can write your own code. And also, we are going to look at ways to handle the data, which means essentially how we normalize the data, some kind of pre-processing. Sometimes the data can come out in different units or scaling parameters. So sometimes you can have wind speed, as we mentioned last time, in kilometers per hour. And the next year it's measured and logged as meters per second, and so on and so on. So scaling the data and having a feeling of how you handle the data is something which often helps the fitting of a specific model. But let's remind ourselves quickly of what we did last time. And you can also see there are some reading recommendations. There's actually a textbook which you can access online. And chapter 5 is actually a very good reminder about the linear algebra, which is needed for calculating derivatives and dealing with many of the quantities which we encounter in machine learning. So as I said, the data which we have is often transformed into vectors and matrices for easy numerical handling of the data. So that textbook is actually pretty good. So let's look at a quick reminder from last week. So one of the reasons why we start with linear regression, I like to call that low-level machine learning, because we end up with a method which is extremely simple to implement, and the optimal parameter are learned by us performing the inverse of a matrix and multiplying that with a null matrix times a vector. So we say we learn the unknown parameters, the optimal parameters, by a very simple recipe. So in a sense, the learning is actually through the equation you are setting up. And then you let the computer find the optimal parameters by matrix inversion and matrix multiplications. So the method is also a method which gives us analytical expressions for the parameters. It also links very well with a statistical analysis, which we will wait a little bit with. So we're going to wait another 2 weeks before we dive into a statistical analysis of ordinary least squares. However, there's something which we are going to enter pretty soon. That means next week. And that is the whole field of gradient optimization. So today we are going to focus mainly on us inverting a matrix and using the analytical expression for finding the optimal parameters. However, this is a kind of unique case where you have an analytical expression for the unknown parameters in terms of known parameters only. It's pretty rare, because in most cases, we don't have a nice and clean expressions as you will encounter in neural networks. So we don't have an analytical solution, which means that we have to use numerical efforts to optimize and find the best parameters which fit the data. And the standard method, I mean, it comes as a surprise to everybody, it's something which is called Newton's method for finding the roots of an equation. So how many of you remember Newton's? Is actually often seen as Newton-Raphson's method. Have you met that? To find the roots of an equation, f of x equals 0. That's Newton's method. Yeah, cool. So we're going to remind you about that. Newton's method is actually a Taylor expansion, where you Taylor expand around a value and you truncate at the level of the second derivative. This is the central algorithm for finding a numerical solution to the optimization problem, believe it or not. And what you end up with is actually multidimensional matrices. And sometimes you don't want to invert or deal with these multidimensional matrices. Actually, the second derivative, which enters Newton's algorithm, is a matrix you have to invert. That matrix is often replaced by a constant. Dealing with that matrix and updating that according to the values of the parameters is something which is really at the heart of all of machine learning algorithms. And you will find methods like ADAM. Some of you may have heard of that. ADAM, adaptive gradient with momentum, which is a paper which was a method which was suggested in 2014, which has in 11 years more than 200,000 citations. That tells you how important the optimization part is. So if you're cooking up a method which is better than ADAM, you're going to get many more friends. And I'm not saying that you don't have friends. but these will be friends which will cite you. So, and we are going to see this in the weeks which come, and this is also going to be part of project 1. Now, the reason why I bring this up as a kind of motivation is that linear regression is something which is very nice to compare with because we have an analytical expression. So when you implement gradient methods, which is a numerical approximation, then you have an exact answer you can compare your results with. So when you are developing the whole machinery and you agree with the exact result, that normally brings in a little bit of confidence in what we are doing, right? So the linear regression has many, many benefits, especially from a pedagogical point of view. And that's why you will see that in essentially all machine learning texts, even though nobody uses that in deep learning methods. However, I'd say if you can make a fit, which is the best one, with linear regression, there's no point in calling a neural network calculation, which is going to require tons of CPU cycles. So if you can use a simple method to fit the data and that gives the best fit, then you use that. Okay? So there's a lot of benefits with starting with linear regression. So what we did last time was actually to define the input data. So can everybody see well in the back as well? So we define inputs and outputs. That's our data. So typically, X is now given as a vector, or it could be a matrix if we have more features. So you could have an input data which deals with housing prices. And then you would have in one specific feature could be the number of rooms, the number of bathrooms, the size of the house, et cetera, which then defines the final price. Then what we have also is the output, and there is an assumption which we are going to make about the data. This becomes important when we are going to bring in a statistical analysis. So we are going to assume that our data, that there exists, when we do regression, a continuous function. We don't know this f of x, but we assume that it exists. And we are making the assumption that this is a continuous function which describes our data. And then we can also assume that there is some stochastic noise in the data. So this is a standard way to approach the data set y, which is the output, given by an input variable x. Okay? Now, when we go to a classification problem, we are going to replace that f of x with a probability distribution. So a probability of getting yes or no. Just to give you an example. If you have many more discrete cases, it could be like the handwritten numbers from 0 to 9. Then you want to have a probability of finding 0, 1, 2, etc. But now, in linear regression, we are going to make the assumption that f of x is a continuous function. Okay? I'd also like to say something more. So we are going to make the assumption that x is not a stochastic variable. So this means that it is its own mean value. We call it unbiased. And it's pretty common to make that assumption because suppose now that you are measuring the position of an object with the speed as input and time. Now, time and speed are variables which you control and you know exactly the value of them. So that means that your x's are well determined. This is the normal case in many experiments. Then there may be some randomness in the measurement of the y's, which you add by this parameter epsilon, which means that the y's can have a distribution and they can be treated as stochastic variables. But we are going to make the assumption that x is not a stochastic variable. Okay? So these are some basic assumptions about the data which we make. They may not be true, but this is the assumption when we are dealing with linear regression. Then what we did was actually last week, was then to assume that this model which we make, which is a y tilde, is now given by some matrix X, and we're going to discuss this in more detail today, times the unknown parameters. So this matrix X can be a matrix of dimension n, the number of data, times P, which is then the number of parameters which we have in our model. So in this specific case, we have P parameters, which we are going to use linear regression to find an optimal representation of. So when we have made a model, we want to test if this is a bad or good model. There are many functions you can use to test that. And you will see that when we come to classification problems, we are not going to use a mean squared error, but the mean squared error is pretty intuitive. It simply measures the difference between the two variables which we have, the output, which is fixed, or target value, which is often called, and the model which we make. And if we have large deviations, the mean squared error will be large because it's squared. Alternatively, we could have calculated the relative error or the absolute error. That's another measure. Now, the benefits here is that this equation leads, when we take the derivatives, it leads on analytical expression. So the function which we end up setting up is this function here, which we then can rewrite in terms of vectors. So this is just a number. So the mean squared error is hopefully equal to 0. So the mean squared error is a scalar, which means that we have to rewrite this quantity here as an inner product, the transpose of a vector times the vector. So what you see here is just the inner product of the differences. And this defines our function, and you can rewrite it in a more compact way in terms of this matrix, multiplied with theta. And then what you want to do then is to calculate the derivatives. If we go down here, so the calculation which we end up with is to calculate the derivatives of this object here with respect to the parameters theta. So when you write them out like this, inside here, somewhere here, there is a theta j. So here we have theta 1, theta 2, and in here there's a theta j. You calculate the derivative, and then you get an xij, and then in here there is a theta j, which now comes just as a theta j here, and then you have the remaining parameters in here. So this is a quantity which we want to calculate the derivatives of, and this is what the expression looks like. And in the exercises, you're actually going to show that this is given by this expression here. I'm coming back to this now. So when you do this, when you have this equation here, you can actually show that the optimal parameters theta are given by the inverse of this matrix times x transpose times y. And what we are going to do now is actually to remind you of some of the expressions from linear algebra, which we need in order to find that expression. So essentially, the expression which you see there is exercise 1 this week. So let me give you some of the mathematical details which you need to look at for solving the exercises. And then obviously during the lab sessions tomorrow, we can keep going on with these exercises. But it's important actually to get acquainted or remind yourself of some elementary matrix vector relations and their derivatives. Because what we are doing now is to calculate the derivatives of a vector. So the expressions, they are pretty compact. Now, it's not given that this matrix can be inverted. And one of the ways to circumvent it is what we call ridge regression, which we will discuss today as well. So the one thing which we need to remind ourselves of, and you may have seen that in linear algebra courses, so y is now simply given by this function f of x, and y and x are vectors. So that means that when we calculate the derivatives of dy dx, this is a matrix. And it's normally called the Jacobian. So that means that you have all these partial derivatives with respect to x0, x1, up to xn minus 1. And then you have the values of y from y0 to ym minus 1. And if now x is a scalar, that means that you would just be left with this column here. So that means that the Jacobian is a single column vector. So it's simply an m times 1 matrix. Because if x is a scalar, you don't have these derivatives here. Then you simply have this column here. And if y is a scalar and x is a vector, then the Jacobian is simply given by this row here. Does that ring a bell, everybody? Have you seen this in some of the math courses you've taken? So this actually forms the basis for what we're going to do now. Okay. So you probably have encountered when you have a square matrix, then this is normally called the Jacobian determinant. So let's take a look at derivatives which you encounter in order to solve exercise 1 this week. So let's just go back to the whiteboard. Let's just bring this up here. So quickly, just as a reminder of the kind of problem we have. So we have a output vector y, which is now defined in terms of y0, y1, up to some yn minus 1. So these are our data points. And y is now a real number, and it is a vector of length n. Similarly, we have x, which is our input, which is now given by x0, x1, up to xn minus 1. And we also say that x is an element of R of n. Then we have the parameters, which are the unknown quantities, and they're given by some theta 0, theta 1, up to theta p minus 1. They're also real numbers. So theta is assumed to be a real number with length p. So this is the kind of basic starting point. And then we are going to make a model now. And the typical model we make, so this is just a model, right? We are going to fit a polynomial of a given degree. So that means that we will make a model y tilde, which also has the same dimension as the x's and the y's. And we are going to make an assumption that this y of I is now given by a polynomial of a given degree. So this polynomial then starts with a j equals 0 up to p minus 1. And then it has these parameters theta j. And it's multiplied with x of I to the power of j. So that means that we have theta 0 times x of I to the power of 0, which is 1, plus theta 1 of x of I, plus theta 2 of x of I. And this continues all the way up to a theta of p minus 1 of x of I to the power of p minus 1. So this is our model. And what we showed last week is that then we can convert the vector x into a matrix. And each column in the matrix represents a polynomial order or feature, as we will call it, or predictor. These are also other names which are being used. So when we did that last time, we could then write a model for y tilde in terms of a matrix x times this vector theta. And this vector x, this matrix x is a matrix of dimensionality. So this is not the same as lowercase p. This is a matrix of dimensionality n times p, and it is given by 1 for the intercept, and then the next one has x0 to the power of 1, x1, down to xn minus 1, and then it continues to x0 of p minus 1, x1 to power of p minus 1, down to x of n minus 1 to the power of p minus 1. This is something which we last time called for the design matrix. This is how we will define our model in terms of a given polynomial. So we rewrite the polynomial in terms of all the unknowns as these columns, which now define this matrix X. And every column is normally called a feature. So in this case, a feature could be the polynomial to degree 2, polynomial to degree 3, etc., etc. Okay? So what we need now is to calculate some derivatives. So for the exercise this week, so exercise 1, so I'm not going to solve all the exercises, but I'm going to give you a kind of guideline for how you can think in order to solve the exercises. So suppose now that you have a matrix, which we call for A. So we have A times X. So Y and X are vectors, and A is a matrix. So A does not depend on Y and X. So if you now look back at this expression here, the matrix X does not depend on the unknown parameters theta. That's important. This is the reason for why we have a linear model, because the X matrix is independent of the unknown quantities. And this feature allows us to find an analytical solution. When we are doing classification with what's called logistic regression, then this is not going to be the case. And then we cannot find an analytical solution as we did for linear regression. So this design matrix, X, is now a case which we now rewrite in terms of A, which does not depend on Y and X. So let's just mark that one. No Y and X dependence. So what happens then is that we define A to be a real matrix of dimension m times n. Y is a vector of length m, and X, and this is the symbol for and, is a vector of length n. So when we now write this out, we have a component y of I. So what I'm using now is actually, in order to see how to calculate the derivatives, it's useful to actually write out the components in terms of a simple expression. So if you now go back to what you had in linear algebra, you may have seen this expression here from j equal 1 up to n. And then we have the matrix elements, aij, multiplied with x of j. Okay? Has everybody seen that expression? I hope you don't get offended if I remind you of some simple linear algebra translations, because now I'm just writing out every component of the vector y in terms of a matrix times a vector. So that means that when I'm now setting up the Jacobian, I need these different partial derivatives. So I need a dy of d of xk. So if I do that, and this is applicable to all k values, which are included in the definition of the vector x, that means that if I do this, I pick a component k here. So that is simply going to give me an aik. And this applies for all values of I and j. I equals 1 up to m, and j for all k in this set here from 1 up to n. Does that sound okay? So if we now are thinking of the Jacobian matrix, which we had on the Jupyter notebook, this simply means that every dy dxk is actually an element of that Jacobian matrix. So that means that if I now want to rewrite this in terms of this Jacobian matrix or Jacobian determinant, if it's a square matrix, then what you see now is that this dy, and now these are vectors, dy of d of x, these are simply given by the matrix A. So just keep in mind that this object here of dy, if we write it out as a vector, is actually given by a dy1, dx1, and then the columns follow dy1, dx2, actually dy2 and dx1, down to dym of dx1, and then we have dy2 here and dx1, and this goes all the way down again until the end. So we have a dy1. Now it's me who's actually messing up here. dy2, this is dym and dx2. So when we then go back, sorry for this mess here, let me just clean up a little bit. So this is a dy1 and this is a dx2. So the columns are the x's and the rows are the y's. So this is just the definition of this Jacobian. And then you see now that one of these elements, ayk, would then be an element in here. So the final result then, when we now rewrite this in terms of vectors, is now given by this matrix A. Okay? So the next thing which is useful to look at is the following. And this is again for exercise 2. So I'm not giving you all the answers. You will actually find the answers in the Jupyter notebook if you just go through them. So the next exercise is to define a scalar. And this is something you will need when you now are looking at, for instance, the calculation of the mean squared error and its derivatives. So we define a scalar alpha, which is given by a vector gamma y, not gamma, but y of t times a matrix A and times a vector x. So again, y is now a vector of length m, x is a vector of length n, and A is again a matrix which does not depend on y and x, and it's a matrix of dimension m times n. Now, how do we proceed here? So one of the things I would be interested in first is actually d alpha. So alpha is a scalar, and I want to write that as a derivative of y as a vector, and I want the alpha of d of x as a vector. So I'm not putting boldface. In my lecture notes, the quantities are boldface, but when I do that on the whiteboard, it looks like a mess. So I'm putting arrows on vectors. Is that okay? And hopefully a matrix, I always reserve an uppercase letter, which means that hopefully from the context, you see that this is a matrix. We are assuming again that A does not depend on X and Y. So we are looking after these two quantities. And one of the things you will need then, and also in the exercise for the calculation of the ordinary least squares, optimal parameters, we need to find these kind of derivatives. So the first thing we are going to do now is to define a new quantity. So we define a quantity which I call W transposed. which is just y transpose times A. So y does not depend on x, and A does not depend on x and y. This is a pretty common assumption in linear regression. Okay, so if we do that, that means that the scalar alpha can be written out like this transpose vector. Vector times a matrix is a vector, times x. And now I'm going to calculate the derivative of that quantity. And I know that if I write this as a vector times another vector, this is the same as a sum over I, and then I have a W of I times X of I. Okay? So I'm just not putting I equal 1 up to the dimensionality. Then I take the derivative of d alpha of dx of k, and that is clearly just going to be wk, because I pick a k in that sum over the i's. So that means that when I want to rewrite this in terms as a vector, this becomes equal to d alpha of d of x vector, and that is simply given by this vector w. So this is a vector times a vector here. So then we have the answer, which is just equal to the vector y transpose times the matrix A, which we defined. Now let's look at the other one. So, and here comes a very important aspect, which is going to be helpful when you calculate the derivative of the mean squared error. So alpha is a scalar. That means that alpha is equal to its transpose, which means again that I can actually rewrite it like x transpose times A of t times y. And then I can repeat the same trick which I did before. And you see now that if I just repeat what I did here, I can define a new vector here. And then I take the derivative of alpha with respect to x or y. So that means that I can now take a d alpha, which is a scalar, with dy. And that's simply going to be given by x transpose times A transpose, the vector. Okay. So another thing we can do, and that is one of the exercises which are going to deal with. So let me bring back the Jupyter notebook, and you will find the hints essentially for solving the exercises this week. So if you will find these examples again. So one of the examples which you need to look at is this exercise or this example. But then if you now take this example which you have here, this yt times x, this is something which is going to be pretty similar to what you do when you do the calculation of the mean squared error, because that is a vector transposed times a vector. And in our case then, what you would do is simply to redefine y minus x times theta. So this is a matrix times a vector, which becomes a new vector. Then you would simply rewrite it like this. And then you can use that example, which I showed you now, because this quantity here is a scalar. So if you then go back to what we had previously, so Wt now, you have to be a little bit careful, because now Wt depends on theta here. So that means that you have to use the chain rule. And then it's pretty easy to show that when you do these derivatives, this is what you get. So that's, I'm not solving the exercises fully. I hope that's okay, because that's part of the exercise this week. But it's useful to get started with the linear algebra, because when we are inputting the data, we have always to rewrite everything as vectors, matrices, or higher order arrays. And these are the quantities which we are going to manipulate whether we deal with linear regression, neural networks, or more complex deep learning methods. Any questions? I can see the excitement here. This is actually, it's not the kind of say most exciting topics, but it has the importance behind these quantities is simply that we have to code them. And if we don't know what's going on, our code may not turn out to produce the correct results. And it's so easy to interchange columns and rows and not keep track of the quantities which we are propagating in a neural network, for instance, that sometimes it can be difficult to trace the error. So this is one of the main reasons why we go through this kind of not too exciting exercises. Okay. There's another quantity which you will also have to deal with. And this is the final exercise, and that is to calculate the second derivative. And you can show that in this case, with linear regression, the second derivative is actually given by a matrix, which is the same matrix which we are inverting in the algorithm. So it's design matrix transposed times X. Now, I just wanted to ask you one thing. So we are talking about optimization. So that means essentially to minimize or to maximize. So when we are minimizing, what do we call the function we are looking after when we minimize? What kind of shape does it have? Yeah? Could say again? No, gradient descent is a method, but you have a name for the function. So suppose the function looks like a parabola with a minimum. What would you call that function mathematically? Yeah?
Convex.
Concave. Okay. So convex is the, when it's, so let me just put it on the blackboard here. So the minimization problem, if you have a function like this, where you want the minimum, you're looking after the minimum, and then this is a concave function. No, sorry, did you say convex? You said convex, right?
Yeah.
Yeah, sorry. This is just me left and right. Yeah? But sometimes I always have to ask myself what is left and what is right. There's a convex function, sorry. Sorry for that. And the maximization problem is a concave function. Okay, good. Now, if you then go back to this matrix, so this is actually a matrix. And this is the second derivative now. So which value or which sign does the second derivative take if you have a convex problem? Is it negative or positive? The second derivative. Positive, exactly. So the derivative is largely equal to 0, the second derivative. Now, this X transpose times X is a matrix. So you can actually say something about the eigenvalues of a matrix if you have a convex problem. Has any one of you heard of that? So if the second derivative is now a matrix, you can actually look at the matrix eigenvalues to infer what the sign of the second derivative is. So if I say that this is a convex problem, you may not have heard of that in linear algebra, but actually you can state that precisely from linear algebra properties of such a matrix. Has anyone heard of that? If I say that the second derivative for convex problem, and you have just a one-valued function like the one on the blackboard, then the second derivative is largely equal than 0. What about the eigenvalues of that matrix, X transpose times X? Have you heard of positive definite matrices? Semi-positive definite matrices? You can actually show, and we will show that to the end of today's lecture, that matrix gives eigenvalues which are 0 or larger than 0. If that is the case, this is also a problem with a unique minimum. And that's pretty neat. So in our case, the second derivative is a matrix, and that matrix plays a very important role in machine learning. It's called the Hessian matrix. Now, for linear regression, like the cases we are discussing now, this matrix has a small dimension. So typically you have, let's say, 10 features, then that matrix would be a 10 times 10 matrix. So these methods are typically applicable when we have much less features than you have data points. Suppose now, on the other hand, that you have, let's say, 10,000 patients, and then you're looking at their DNA for signals of what could be the reason for that specific disease. Now, when you look at the DNA, you can have millions of features. In that specific case, that matrix would be million times millions. And then it's not so easy to introduce these methods, because then you would go beyond of what you could typically store in standard matrix inversion algorithms. So these methods are pretty good when you have few features, and that means from 1,000 up to 10,000, because then you can invert the matrix easily. You can parallelize and still do it, but it will take more time. So this matrix, if this is a convex problem, this matrix is then a semi-positive matrix. So let's move on a little bit, but I see now that I went a little bit over time here. Actually, I stole 2 minutes of your break. So I should give you back another 15 minutes. So we begin at, let's say, 3:17, if that's okay. We'll take a break. Sorry for forgetting time again. Okay, so let's try to start again. I hope you all can hear me well in the back. That sound is okay in the back? Okay, good. So before we go back to some of the more mathematical, not derivations, but mathematical analysis of linear regression, let's look at some examples and things which we will repeat again and again during the lab sessions. So I wanted to show you how you, instead of using scikit-learn, which we had in the exercises last week, how we can write our own code. And this is pretty straightforward. So what we are going to do now is to do things in a pretty brute force way. We are going to set up a model which fits a data set which is given by a second order polynomial. And you have seen this data set last week. So it's exactly the same one. And but we are going to be a little bit more ambitious, and we want to fit a fourth order polynomial. So the data set which you have here is the same one which we encountered last week. And in the beginning here, we can just take away the noise. So we just assume that this is a second order polynomial. So what we can do now, as you can see, we can set up the design matrix. So I want to fit a fourth order polynomial on a second order polynomial. That's not very smart of me, but let's assume that I don't know what y is. And I say, okay, let's try a fourth order polynomial, okay? So what you see now is that I am defining my design matrix. So this is the first column, and this is just one. The second column is x. This is the vector x. The third column is x squared, because we are trying to implement this model. This is my model. You see the y tilde. Then this is the third order part, and this is the fourth order part. And this sets up the matrix X. And here's how, if you don't want to use scikit-learn, now we're using the whole data set. And we are calculating the inverse of the matrix. So this is our theta hat, I mean the optimal parameter. And you can see now that theta here is simply given by the inverse. We are assuming that this doesn't cause any problems with calculating the inverse. So this is matrix X transposed multiplied with matrix X. Then I multiply with X transpose, and I multiply with Y. And if I do that, then I can alternatively use a Python function in NumPy, which is called least squares, which does everything for us. So I could rerun that one. Then I could calculate the error. And there's a quantity which we barely discussed last week, which is called the R2, which we will come back to. But then you see the, if we just run this one, and then we print it. So the ideal here is that this is equal to 1. And now if you look at the mean squared error, this is almost 0. So when you have 10 to the minus 15, that is 0 to numerical precision. So 10 to the minus 23 is pretty good. Now you're going to see something a little bit different. If I now change this to a second order polynomial, then I'm just going to have 3 columns. So I'm doing this a little bit manually here. And then I repeat it. So now I should actually get, so I get 1 here. But if I look at this one, 10 to the minus 28. So I actually, when I imposed a 4th order polynomial, I got an error, mean squared error, which was not as good as the one when I have exactly a 2nd order polynomial. 10 to the minus 28 is basically 0. So is also 10 to the minus 23. Now, if I am a little bit less smart, and suppose now, so let's do this manually. I could now do X, and then I do 10, and I do a 6th order polynomial. Now, a 5th order polynomial. And then I can just repeat this one. Well, let's just change it. So I have 8 columns where I include the intercept. Now, if I want to fit my function now, so let's just calculate the mean squared error. And now you see this is 10 to the minus 15. So what you will see now, if I go to, let's say, if I have 100 points and I go to a 99th order polynomial, that mean squared error can become huge. So this is an example of something which we are going to discuss pretty soon now, which leads into what's called underfitting and overfitting. Okay? So if I knew that my polynomial is exactly a 2nd order polynomial, I could extract the parameters immediately. So let's look a little bit more on this kind of playing around. You can also define the relative error if you want to. That's another. And you can see the relative error here is also pretty small, 10 to the minus 8. If I were to use a 2nd order polynomial only, suppose now I take away all these guys here. And I just rerun everything. When I add noise to this, then I'm going to get a result, which is, and in this case, you see that the relative error is basically 0 here. Now, one thing which is pretty common is actually to split your data into train and test. And there is a functionality in scikit-learn, which is called train test split, which does it for us. Now, in the Jupyter Notebook, you will find an example on how you can write it yourself. But as we said last week, we would typically recommend to use the functionality which is included with scikit-learn. So you don't get a deeper insight if you rewrite a new program for testing and splitting your data. Now, the reason now is that except for these simple examples where you can produce new data continuously. So I could train on 100 data points, and then I could generate new 100 data points and test it. So the idea now is that you are going to take some of the data and use that to train the model. Then you leave out some data which is not included in the training. and then you test it on that data. Because you can quickly have outliers in your data, which can mess up the prediction which you want to make. So you are training a model which you want to use to make predictions. And you want that model to be reliable. So you can go to your friends on a Friday evening at a party and you can say that this is the best model you can get. By the way, I have a suspicion that's the reason why nobody invites me for parties anymore. It's a joke. Okay, but the thing is that splitting the data in train and test is an essential element in machine learning, because in essentially all cases, the data you have is what you have. So train test split is actually a functionality which you will find in scikit-learn, which is here, train test split. So again, the same exciting data set. We are fitting in this case, a fourth order polynomial, but now we split everything in train and test. Now, there is no magic number for doing that, but most practitioners, they typically include 60 to 80% of the data in training, and the rest is then left out of the training and is used to test your model. Now, here, in this simple case, as you can see, I could generate new X's continuously, right? So I could train a model on all this data, and then I could simply say I produce a new data set, and I test it. And that data set is different from the one I use in training. So this is what normally we call vanilla models, because you can easily produce new data. But in real life, when you make an experiment, and if that experiment runs for half a year or a year, it's very unlikely that you will be able to rerun the experiment if something goes wrong. So you can say that the data you have is what you have. And in this case here, you can see now that what we are doing is that we are calculating the parameter theta, and this is done on the training data. You see that? Only on the training data. So we split it, so it returns an X matrix, which contains, let's say, 80% of the data of the X values, and a Y train, which contains 80% of the outputs, and then you have the remainder in X test and Y test. Now, the theta value, the optimal parameter, is now based on your train data. So this is our own code where we invert a matrix, and then we make a prediction for training. You see that? That's the error which I will get when I train. Okay? This is my prediction with the training I've done, and then I can use that to calculate a mean square error. And then I can repeat that because I have the optimal values theta. And the optimal values theta, I can use them to generate a prediction for training, but I can also use them to define a prediction for the data which is in the test set, which was not included in training. And this is X test times theta. So just to remind you of what we are doing here, so let's just go back to the whiteboard. So if we go back to the whiteboard, so what we are doing now is that we have split the data into training and test. So we can say that we produce a Y prediction, Y predict on the training data, which is then produced by simply taking X train multiplied with the optimal parameters. Then we have a Y predict on the test data, which was not included in training, which is simply X test. This was left out, times theta. So theta is something we find from training. So the theta value now is simply given by us calculating the inverse of the train set times X, so this is the inverse, times X transpose of train multiplied with Y train. So this is all Y tilde, but we have different predictions we make. Okay? So we train on obviously the train data, and that gives us theta. And then we are hoping that this theta is going to give us an equally good result on the data which was not included in training. And these are the lines which you see in the code here. So let's go back. I've also included the R2 score, which we haven't discussed yet, so just let's leave it out. And if I do this now, what you will see is the following. So in this particular case, I have some noise as well. But if we take out the noise again, what you will see, since we are fitting a fifth order polynomial, is that, okay, we are fitting a fourth order polynomial. You will see that the coefficients for the first order here, the third order and the fourth order, they are close to zero, but they are non-zero. So the function which I'm feeding in should give me 2 and 5. But it's giving me 2 to some numerical precision and 5, but then I have some junk here, which ideally should have been equal to 0. But it is not, because I'm fitting a fourth order polynomial to a second order polynomial. But still, you see now that the test or mean squared errors, they are basically the same here. So there's not much difference. Here's an example of making your own train test. But let's now go back to some of these things here, and let's now look at another example. So what I'm going to do now is to, and this is one of the exercises this week, we are going to try to reproduce a figure which is in this textbook here. You have access to this textbook. So we are going to define X to live between -3 and 3, and we are going to produce 100 data points. And our data set is X from -3 to 3. And we have a function which is an exponential with an argument X squared, plus another exponential with X to the -2 squared, plus some random numbers. So we know that in principle here, if you think of the Taylor expansion of exponential, we should have an infinite order polynomial, okay? So what I'm going to do now is to use one of the things we had last week, where I use now scikit-learn and the polynomial features of scikit-learn. So I'm not constructing the design matrix by hand. I have another program below where I'm just setting this up by making a loop. So in the previous case, I just did it by hand, order by order. Now I'm just going to use polynomial features in scikit-learn, which you see I import here. And let's now, let me just send it here. We could change this a little bit now. So let's say we do 100 points and we want to do a 15th order polynomial. Now I'm going to set up a test error and a train error. I define the polynomial degree. I split my data. 80 data points are going to be train, and 20 data points are going to be the test set, which is not included in the training. Here, I'm scaling my data, and I'm coming back to what that means. So let me just show you this example first, because this is a very important example. Here I set up the polynomial features. I'm setting up linear regression. When you set fit intercept equal false, it's the opposite of what you think. It means it leaves out the intercept. So the intercept column is not included in the fit, because you can, in linear regression, you can recalculate that. I will show you that during one of the lab sessions next week. But it's a little bit counterintuitive, because you would think that fit intercept false means that you actually don't take it out. That's the way I was thinking. But then what I'm doing now is to perform a loop over the polynomial degrees. And I'm comparing my prediction in the test error here. This is the mean squared error, which I'm calculating here, as you can see. NP mean, numerical Python, mean value. I take the Y test minus the Y prediction, and Y train minus Y fit, which is what I get from the training data. So this is training data, and this is the test data. So if I run this code, we are going to see something like this. So what you have on the x-axis is the order of the polynomial. And you see now that the train error is getting close to zero. It can become closer and closer to zero because you can fit to perfection. Okay? And this is essentially what you see. But then you see there's a tendency here that your test error is normally always above the train error. You obviously have less data points, and you're making a prediction. Now, I could say, okay, this looks pretty fine. Let me now become more ambitious. I know this is an exponential, so let me fit a 30-fold polynomial. So this is something we can run easily. And you're actually going to do this in one of the exercises this week. So let's say that we fit a 30-fold polynomial. Just rerun. And now you see this, that the error is increasing on the test data. So this is an example of what we call overfitting. So when the test error starts increasing, that's when we have reached a model which is actually going into the region of overfitting. So the prediction we make now is going to be on data which will actually give us a mean squared error, which is larger, because we have many outliers from the model. So I am training to perfection, but now you see that this one is now starting to increase. I could change this if suppose now I give more points. So this picture changes depending on how much data you have. So this is not a stable picture. If I run with 1,000 points, it's going to look like this, because I have much more data in the training, and the more data, the better the training, normally. And that means also that the test data, which I'm having now, has a lot of data set, and the influence of outliers becomes less important, because I'm actually calculating an expectation value, mean value of the mean squared error. Now, in the weeks which are coming, we are going to discuss this from a statistical point of view using something which is called the bias variance trade-off. So when you do machine learning, this is actually one of the things which we always have to take care about. So people will always ask you, are you overfitting? Are you getting a too good fit to the data? How does it behave on data which was not included in the fit? So you see from this model here that clearly if I have few data points, then it's very easy to overfit. So if I go to, let's say, 70 points here, then this may actually explode here, as you can see. So what we are looking after is some kind of region where the test error is still decreasing, but then where it starts increasing, that would be the region where we have found the optimal model with that data points, number of data points. So to summarize, you can overfit or you can fit a model in the training data to perfection. And that is seen in the training error, which just flattens out and goes to zero. But then you have outliers in your data set, which was not included in the training, and that can easily lead to a mean squared error on the test data, which is much, much worse than the one you have in the training. So This is a typical thing which people often use if you don't do the bias variance trade-off, is simply to check if your model is overfitting in this way or not. So when you find a region where the complexity of the model gives you now a test error which starts increasing, that's a flag that you're now overfitting. So we have not gone into the mathematics here, but this is one of the exercises we're going to deal with this week. And it's just to get a feeling of what can happen when you're trying to make a too good model in the training set. Any questions so far? So in 2 weeks, we are going to introduce a statistical interpretation, and then we are going to look at in detail the bias variance trade-off in order to analyze the point where the test error starts increasing and to have a kind of measure, a quantifiable measure of when we should stop. But keep this in mind that this is something we have to live with because you will always have a limited data set, except for these vanilla cases where we can just generate new data whenever we want. Also, the data set which we had here included a noise. If you take the noise away, then what you will see is obviously that the results are much better. So if you have a lot of noise in your data, then it's much more difficult to fit a good model. Whereas here, now we have just an exponential, and we know that when we go to, let's say, a 10 or 15 order polynomial, that does a pretty good job in representing an exponential. And this is what you see here, right? So my recommendation is always to play around with the codes like these, because that helps us in gaining some kind of insights about how these different models function. And it's always useful to play around with simpler data sets, with and without noise. Any questions? Okay, so let me go back a little bit here. And I'm going to, oops, my Jupyter notebook disappeared here. Huh? What happened here? Well, it just restarted. Now, there is a topic, just a technicality, which I want to mention before we move into the mathematical interpretations. So one thing which you would typically do then when you run these machine learning codes is actually to pre-process your data. And this is pretty common. One of the standard pre-processing is called the standard scaler. So what that does is that it takes out the mean value of every column in your design matrix. The hope then is that your data will be a little more compact by subtracting away the mean value, which means that you have less scatter in the data set. You subtract the mean of each column, and that means that hopefully there is less scatter in the data. This is something which is done almost by default when you use scikit-learn, but it's called standard scaling. This depends very much on your data. As I said, you can have data which come in specific units, which can make your data points large. And then you would like to scale them down to, let's say, a domain from 0 to 1. Because then if you have a small scatter in your data, then it can be easier to fit. There can be problems like loss of numerical precision, etc., etc. You're inverting matrices, you're multiplying matrices with each other. And this is a mathematical operation which easily can lead to accumulation of errors. So it's pretty common to do some scaling on your data. So the most common one, and scikit-learn has all this baked in for you. So one of the functionalities is called the standard scaler, which actually subtracts the mean in each column of the design matrix. So it has the drawback that it does not ensure that we have a particular maximum or minimum, There's another function which is called min-max scaler, which ensures that all the features are between 0 and 1. So that's a way to scale your data, because you can have variables in each column which vary a lot. Just think of this polynomial fit. If I have x between 0 and 1, then I know that x to the power of 1 will be numbers between 0 and 1. If I have x squared, then you know that 0.1 becomes 0.01. So clearly the numbers become smaller. And if I cube them, it becomes even smaller. So what's often done is to try to have roughly the same scales for all the features. It's not always possible. So min-max scaling is something which is pretty common. We have other types of scaling, which is called a normalizer. We have something which is called a roboscaler. You can actually read them up. But the most used ones is the standard scaler, where you take a specific column, J, and then you subtract from that the mean value of that column, and you divide by the standard deviation. If you don't want to use a standard deviation, which could by accident be close to 0, then it's common to set that one to 1. If you divide by the standard deviation, then you're making the variables dimensionless, yeah?
Also wondering if the scalars
Yeah.
always are linear, or if you would have a like logarithmic scaling.
You can also do that. So you have actually, this is a very good question, because we can have scalings which can be nonlinear, which transform the data in a very smart way, which makes it easier to make a fit. So let me show you an example of that, because that's a very good question. So the kind of scaling you do depends a lot on the data set. So here's a scaling which, for a classification problem, is actually very useful. So this is a classification where you have distinct classes of objects. So let me show you that, where another scaling than the linear ones can be useful. Suppose you have a binary classification problem, and your data, so you have the crosses are here, and then you have circles here. And then you have Y here and X here. Now, if you want to make a classification here to distinguish between crosses and circles, you see it's difficult to define planes which separate clearly. But what I could do now is to square my data points. So if I square my data points, what happens then is that I could now get these guys here if I take the values of them. So this is actually, so I could get these up here if I square them. And then I could have a plane here where I have the smaller values here. And then I have these values here. And then I know that I can have a straight line which separates the two. So then I just need a smart algorithm to find that straight line which separates the two classes. And that line is then used as a kind of model for, say, that if the value is below that specific value, then it's crosses. If it's above, it's circles. So that's a classification problem where I have scaled my data. So you're not limited to, let's say, subtracting the mean value or projecting it down into, let's say, 0 and 1, or have an X min and X max. So it's actually the insight you guys have about the data set which plays a role here. Good question. So let's go back. So the standard scaling here is an example where I've taken the pandas again, just to show you how it functions. So I'm setting up a 10 by 5 matrix. I have 10 rows and 5 columns, and just given by random values. And I like using the pandas, so I define a matrix here by a panda data frame. I write it out, I print the mean value, I take the standard values. So my standard scaling is actually taking the columns and subtracts the mean value. This is what it's doing. Then I'm actually comparing that with what scikit-learn is doing. So standard scaler, which you see here, is a function of scikit-learn. Okay? And then I have false standard deviation. So I don't divide by the standard deviation in the formula which you saw here, right? So because I divide with the standard deviation, if I put standard deviation false, it doesn't do that. And then I'm simply taking the difference between what I did manually and what scikit-learn is doing. This is the original matrix. I have 10 data points and 5 columns. This is the mean value of every column, the standard deviation. I subtract the mean value, and then I take the difference between scikit-learn and my handmade stuff. And you see that these are zeros. So essentially what scikit-learn is doing for you in this specific case is actually to standardize or subtract the mean value. And the hope then is that there is a less large scatter in these different values for each column. Yeah. Hey, could you say it again?
Is any one of them has a faster runtime than the other one? Is any of them or less?
So the scikit-learn library is normally optimized to run on GPUs and CPUs. So, but I guess for this small matrix here, you won't see any difference. Yeah. But the reason why I normally recommend using scikit-learn is that that interfaces nicely with all the other machine learning libraries like PyTorch and TensorFlow, etc. So use this functionality. And writing this kind of subtraction again and again is actually not something which gives you deeper insight. So it's pretty common to actually use this standard scaling on your data. It may not improve the fit, but it's something which is normally done by default. Let's see, we have some questions in the chat here. And okay, that's the... Yeah, that's correct. That's correct. Yeah. So, yeah. So the model, this is a very good point in the chat here. I don't know if you've seen it. When you ask to play around with a model, you're really referring to model design or statistical modeling. But in reality, the model also depends on independent and dependent variables. So it's not just a sandbox. So we can say that the model has two phases, one that we construct deliberately and one that emerges from the data itself. That's a good observation. Okay, so one of the things I wanted to do now is to, after we've done this kind of tests here, is to go into the mathematical interpretation of what the ordinary least square is doing. So before we do that, I wanted to say a little bit about two other methods, which we are going to discuss in more detail next week. And these two methods, before we dive into it, so I was a little bit optimistic. I was actually hoping to do that. If you look at the matrix X transpose times X, when can I not invert this matrix? What kind of properties would you look after when you cannot invert it? Yeah.
When the determinant is 0.
When the determinant is 0 is one of the properties. If you look at the matrix, you want to calculate the determinant of. What does it mean that the determinant can be 0? If you think of, let's say, a column vector, yeah? Yeah. So if you have two or more columns which depend on each other, then you cannot invert the matrix. Now, when we are doing a polynomial fit, every column represents a polynomial to a different degree. So if you calculate the norm of two separate columns, that is guaranteed to be 0 or close to 0. So that means that they are independent of each other. But in most data sets, there is a dependence. So the polynomial case we've been looking at is a kind of ideal. It normally is a painless approach in the sense that the matrix which we are ending up with is invertible. So back in the 60s, there was a simple trick to make the matrix invertible. Can you figure out what kind of simple tricks you could use to make a matrix invertible? Anyone has seen that? You will often see that in many old linear algebra libraries. There is often a variable called 0, which is defined to 10 to the minus 10 or something. So what you could do is to add a non-zero number along the diagonals. That's a trick to invert a matrix. But in principle, you are solving a different problem. But the matrix can be inverted. And then you're hoping that this small value you add to the diagonal elements doesn't change the problem that much. So this is actually a trick which was used widely. And this leads us to another method, which is called ridge regression, but which we can reformulate in a much nicer way and obtain the same result. Okay? So the method which I wanted to introduce to you, so I'm just going to skip some of these. So this is the way you would fix the singularity. So you simply change the matrix that way. That's a cheap and dirty trick. And as I said, you will be surprised to see that this is used in many numerical algorithms. However, if you look at that expression, you can obtain the same if you now introduce what's called ridge regression. So instead of optimizing, so this is what we have done before, and you can write this in a more compact way, like a norm2 of a vector squared. So the norm2 of vector mathematically is defined like this. The norm2 squared gives us back this expression of the inner product of two vectors. This is a vector and this is a vector. Now, what you could do now is to optimize this problem you see here. And this is called ridge regression. That introduces a new parameter. And we are coming back next week to the mathematical discussion of what this means. So there is another norm you can use, which is called the norm 1, where this quantity here, this one, is nothing but the sum over the absolute values. So this introduces a new parameter. So when I take the derivative of this expression with respect to theta, I'm going to get what's called ridge optimization, where the only thing I need to do now is to invert a new matrix. So if you take the derivative, and this is actually in the exercises, if I optimize this problem, and this lambda becomes a hyperparameter. And this is where the disappointment kicks in for many of you. Because at the end you say, hey, well, what we are doing, we're just tuning lots of parameters. But this is a new optimization problem. So in 2 weeks, we are going to look at the statistical interpretation of this. And you can actually give it a very nice statistical interpretation about the way these y's are distributed. But we are coming back to that. But now it suffices to say that what we are doing is to optimize a different problem where we now have introduced another parameter. So how many of you remember from mathematics Lagrangian optimization? Did you solve, for instance, a problem where you use Lagrangian optimization to show that the shortest distance between 2 points is a straight line? Has anyone done that? That's a classical problem. So what you can think of this is a Lagrangian optimization problem, where you add an additional term. When you then run through the derivatives, you get an expression which you would also get if you just use a simple trick of adding a non-zero value to the diagonal matrix elements. Then that matrix is invertible, we have solved all problems. We can go quietly to bed, relax, because now we have a matrix which can be inverted. The problem is that this lambda, the value of it, can actually make some of the parameters disappear. So it's actually a way also to tune away parameters of a polynomial expansion, for instance, which are less important. So we are to the end today. I was hoping to cover a little bit more, but what we are going to do next week is to look at the mathematical analysis of what this new parameter actually means and how we can interpret it. So there is some material in the slides here, which we're going to repeat the first lecture. And so take a look at the material today, because we're going to use some of it next week, in particular about the singular value decomposition, because that's the tool which we will use to analyze what is happening. But you can think of this as an optimization problem with additional parameters. So you're optimizing a different function. And this often can give a better result. But you don't know in the beginning whether this is the case or not. But the cheap trick is something we can formalize in a nicer way than just as a cheap trick, the way it was introduced to circumvent the non-invertibility. Okay, we stop here. Is that okay? Have a nice week, all of you.